I'm going to talk about repetitive motion. By repetitive motion, I mean motion in which an object or objects move in a pattern over and over again. All right? So, for example, imagine some weight suspended from a spring, okay? And the weight is moving up and down, over and over again. Okay, so that's an example of repetitive motion. Think about a moon moving in a circle around some planet. It's moving in the same circle over and over again. That's another example of repetitive motion. What about the end of a pendulum moving along some arc of a circle, right? Isn't the pendulum repeating the same pattern over and over again? All right, so all of those are examples of repetitive motion, and we are going to learn about some parameters to describe different types of repetitive motion. Imagine that we plotted some functions that corresponded to examples of repetitive motion. So give me a minute or two to make a drawing, and then we'll continue. All right, almost done. All right, so on the left, I have a picture of a pendulum with a red weight on the end, and I've also defined an XY coordinate system with the y-axis being the center vertical line with respect to the pendulum's motion. All right. Now, on the right, I have a picture of a a moon moving in a circle around a planet, and I've defined an XY coordinate system with the origin at the center of the planet, and I've also defined an angle theta that corresponds to the position along the circle of motion. Okay? Corresponds to some position along the circle of motion. Now, what would the evolution in time of the x value for the pendulum look like? All right. Well, the x value goes from some biggest positive value to some extreme negative value, and then it keeps moving back and forth between those two extremes, right? So for the pendulum, you might guess that the graph looks something like a cosine or sine function plot. Okay, something like that. Now, for the planet, what do you think theta would look like plotted as a function of time? Now, I'm going to define theta to always be between 0 and 360 degrees. Okay, so once the moon crosses the x-axis on its trip around the circle, then the angle, the theta, will go back to 0 again. So the way that I've defined theta, the theta will grow up to 360, and then it'll go back to 0, and then it'll grow again up to 360, okay, and then go back to 0. All right. So it'll look something like this, right? Now, notice that for both of these examples of repetitive motion systems, notice that the corresponding graphs, okay, are what's called periodic. In other words, both of these graphs, you can take some portion and copy it over and over again and recreate the entire graph, right? So, for example, for the pendulum, the x versus time graph, you can see that you have little mountains or valleys, okay, take your pick, and you just copy those over and over again. For the theta versus time graph for the moon planet system, you've got this slanted line, right, and you just keep making copies of those lines. Okay, so you'll notice that for any repetitive motion system, you can plot some corresponding function and get a periodic graph, okay? Now, I said that the periodic graph has a portion that you just copy over and over again, okay? Now, that portion that you copy over and over again is going to have some width, right? So for the pendulum graph, if you keep copying the mountain over and over again, we can talk about the width of that mountain piece, okay? And for the moon planet system, the slanted line, that has a width, okay, with respect to the horizontal axis. So we could measure that width. Okay, and that is called the period. Okay, so for repetitive motion, we can define a period. Now, let me show you some examples. Okay, so let's say that the pendulum took 1 second to move from one side, from one extreme of its motion, from one side to the other, to the extreme on the other side. Okay, so it takes 1 second to go from right to left or left to right. So what would be the period? Okay, so the period, can you see that the period would be 2 seconds? All right. The mountain, notice that the mountain in my drawing, okay, on the x of t graph, the mountain includes, when you're going up the mountain, the end of the pendulum is moving from right to left, and as you go down the mountain, it's moving from left to right. Okay, so it would be 2 seconds. You have to do a whole, what's called a cycle, all the way to one side and all the way back. All right. Now, for the moon planet system, imagine that it takes a month for the moon to go around the planet. Okay? then the period would be a month. All right. At the start of every month, the planet's in the same position it was at the start of the previous month, ready to repeat its pattern. Okay. Now, what about for our planet Earth going around the sun? What's the period there? I hope you would agree that it's 1 year, right? What about the seasons? Okay, you can plot the temperature in your city as a function of time, and the temperature will go up and down. It'll look a lot like the x of t graph that I have there for the pendulum. Okay, it might be raised a little bit if you're plotting temperature versus time, unless you live someplace that has an average temperature of 0 degrees Fahrenheit. All right, but what would be the period of the temperature evolution in your city? Can you see that it would be 12 months? Because every 12 months, chances are the behavior of the temperature in time is back to what it was 12 months ago. All right? So those are some examples of periods. Now, another thing that we need to define is what's called amplitude. So for the graph, the x of t graph for the pendulum, notice that the x values they have a maximum positive and a maximum negative value. Okay, we can define the maximum deviation from the center. Okay, so this distance, or you might say the height of the mountain, okay, that is referred to as the amplitude. All right, so if the maximum distance of the pendulum from the center is 4 centimeters, then the amplitude is 4 centimeters. Okay? Suppose I'm jumping up and down over and over again. All right? And suppose that every jump is, let's say, gosh, what's an average length, height of a jump? Let's say it's half a meter. Okay, so I'm jumping half a meter up in the air, back down, up and okay. And let's say we plotted my height versus time. What would be the amplitude for a half-meter jump? Okay, now for that example, the amplitude, you might think that the amplitude is a half meter, because I said that I jump a half meter in the air, but actually it would be a quarter of a meter. Okay, let me show you why. Okay, now let's focus now on the moon planet system. Can you see that the graph is not centered with respect to the horizontal axis? Okay, it's actually centered with respect to a different, what's called a center line. Okay, like that. All right, so the angles are sometimes the measures of the angles are sometimes as big as 360 degrees and sometimes as small as 0 degrees. All right, but they're the center. What's the number between 0 and 360? It's 180, right? So we have to define the amplitude with respect to the center, which is 180 degrees, corresponds to 180 degrees. So the maximum deviation from 180 degrees, so it is 180 degrees. It's 180 degrees difference to go from 180 to 360 or from 180 to 0. All right? So if you wanted to make a picture of the distance you need to measure for the amplitude in that example, I would draw this. Okay, and so that's the reason for my half-meter jump, that the amplitude would be a quarter meter, because when you plot it, you would have some situation like this where when you plot the height versus time, the center line would be raised. It wouldn't be the horizontal axis. Okay, so there's another example of the amplitude with respect to a periodic graph. And then the last parameter we need to define is it's related to the period. The period asks how long is the width, okay? Now the frequency asks how many periods do you have within some unit time. For example, in 1 second, how many periods do you have? So we're going to define the frequency this way. The frequency is equal to 1 divided by the period. Okay, so it's the inverse of the period. And those are the 3 parameters we need to know: period, amplitude, and frequency. So if something moves in a circle, let's say it completes a circle every 2 seconds, okay, then the frequency is 1 divided by 2, so it's half of a cycle every second. You see how I inverted the 2? Okay, now let me mention one more thing. The period is often denoted by capital letter T. The amplitude is often denoted by a capital letter A. And the frequency is often denoted by the letter F. So all of that is to say that the last formula that I wrote down there, you can write that more compactly this way. F is equal to the inverse of capital T. All right. Now, let's do some examples of calculating frequency. So, what is the frequency of an ice skater moving in a figure 8 if it takes 5 seconds for the ice skater to make a single figure 8? Okay, so think about that. So the period is 5 seconds, okay, and the frequency would be the inverse of that, so 0.2 cycles per second. And a cycle means that pattern that's repeating, the period, okay. Now, because we write cycles per second so often, there's actually another name for cycles per second after in honor of a famous physicist. Okay, so we refer to the units of frequency as hertz. So for this ice skater, we would say that the frequency is 0.2 hertz. All right. Now, what about something that had let's say something that happened really fast? So maybe some information is coming down a wire over the internet, okay, copies of it over and over again, and let's say that the data keeps being retransmitted every 0.1 seconds, okay, so the period is 0.1 seconds. All right, what would be the frequency for that example? All right, so for that example, we would invert 0.1, and so we would say that it's 10 hertz. Okay, now there's one more thing that I need to clarify. So I've hopefully made it clear that the corresponding graphs of repetitive motion systems can have lots of different shapes, okay, lots of different shaped pieces that are copied over and over again. Okay, if the corresponding function graph for a repetitive motion system is a sine or cosine function, or it's some transformation of a sine and cosine function, then we say that the motion is simple harmonic. All right, so for example, for the pendulum system, remember we sketched the variable x as a function of time, and and we said it looks somewhat like a cosine graph. All right, so the pendulum is a simple harmonic system. Okay, let me type that out. Simple harmonic motion, or simple harmonic system. All right, now I also mentioned that if you plotted the temperature for your city versus time, that the temperature would look something like a transformed sine graph, right? It would be raised, probably, unless you live someplace really cold. So that is, you might say that that's approximately simple harmonic. Okay? A mass moving back and forth attached to a spring, that undergoes simple harmonic motion. Okay? So whenever there's a corresponding function that can be described in terms of a sine or cosine function, we say it's simple harmonic motion.